Okay, welcome back to EE 631. Can you guys hear me?
Yes, we can, Professor.
All right, very good. Yeah, so today I turned the lecture to online, yeah, mainly because of the Super Bowl parade. So hopefully that none of you need to deal with the traffic. Yeah. Okay, I hope nobody show up in the classroom. I sent out an email this morning because I just realized that this morning when I received the email from the university. Okay, so we should be giving out homework 2 very soon, if that's not already on the website. So just keep that in mind. So you should be able to get the second homework very soon. All right. Any question before we start?
So we will not have class next Monday.
Next Monday. Yeah, I heard that's a holiday, right? Is that right? Monday. Yeah, I think that is correct. I think Monday there's no class. But you guys should check the USC calendar. Yeah, I heard today that Monday there will be no class. So did anybody have a chance to check on Monday?
I think at university calendar it's marked as the President's Day, so.
Okay, so I think that's really a holiday. Yeah, so I think no class on Monday. Okay, very good. Any other question? All right. If not, let's continue on the sampling circuits. So on Monday we, kind of went through a few non-idealities related to the sampling circuits, and today we want to take a closer look at the so-called clock jitter. Okay, so basically what's going on here is that remember that when we talk about the track and hold circuits, and we said that there's a clock, right? Remember there's a clock coming in, and then this clock basically should be ideal square wave, and then you should always have a fixed period, right? The fixed period, for the clock. However, in real life, this clock, will have noise, right? Will have noise. So what happened is that, if you look at this rising edge here, sometimes you can rise later, sometimes will be rising earlier. And likewise, when you are falling, sometimes you will be falling earlier, sometimes you will be falling later, right? So essentially, what we can think of is that, whenever there's a transition edge with a clock, there's always a certain region that it can deviate, right? It can deviate from the ideal position, right? From the ideal position. Okay, so this can create some problem because do you remember that I talk about when is the sampling instant? So let's say if this is a MOS sampling switch, when is the equivalent to the sampling instant? Right, so it has to be going from the tracking mode to hold mode, right? So when you go from track to hold, that folding edge, mark your sampling instant, right? So in the ideal noiseless case, there's no problem because all the spacing are the same. However, because of the clock jitter, right? So this sampling instant, sometimes will come a little bit late, sometimes will come a little bit earlier, right? So you can see that, basically this delta function, has some uncertainty, right? But at least, when the clock finally do the transition, it will still behave like a delta function, right? So that part remains the same. So the only thing that's different is just that sometimes it will be earlier, sometimes it will be later. Okay, so what is the impact, right? So here you can see if this is my input, right? So the black signal here is my input, And then I'm supposed to, sample, right, by this delta trim. So the blue one is actually the delta trim, right? So supposedly, I should sample this point and this point, right? So whenever you have this sampling instant, that's where you should really take a sample. However, because of the jitter right now, as you can see, there's a delta t right there. So what ends up with that, you can sometimes end up to be this point, sometimes you end up to be this point instead of the red cross point, right? So if you look at that error, right, or the voltage difference between this green dot, which is the actual sample, versus the red cross point, that we can say that's the error induced by the clock jitter, right? Induced by the clock jitter, right? So that's basically the voltage. Now, in order to estimate, what's the magnitude of these errors caused by this clock jitter, what what we can do is that we can do this first order approximation. So how do we do first order approximation? So what we can do is that first of all we can take the first derivative at that sampling instant, the nominal sampling instant. So if I take the derivative across, around this red cross point, you should get this, right? You should get this straight line, right? So that's a slope. That's a slope, around the sampling instant. And then what you do is that, you multiply the slope of this linear approximation line with the delta t shift, right? The delta t shift, is basically on the x-axis. You have a delta t, and you multiply by the slope, and that will give you the amount of voltage deviation in the y-axis, right? Does that make sense? So basically, this is a linear approximation of the jitter-induced errors. And therefore, as I show you on the left side, right, you can pretty much approximate this delta V as dV dt, right? And this V is the input signal, right? V in, so V in dt. So you take derivative multiplied by delta t. So that's the induced errors. Okay, so here's a question, right? So when I design the ADC, I understand that right now, because of the sampling clock has uncertainty, right? So it has jitters. It unfortunately give me additional errors. So so when I did design the ADC, how should I find the tolerance of this delta V? So to what level that we can tolerate this delta V?
Less than 1 LSB.
Exactly, right? So that's exactly what I was mentioning before. Whenever the question I ask you, if you just tell me 1 LSB, that's probably 90% it is correct, right? 90% is correct. So just less than 1 LSB, and that'll be good. Okay. Okay. And one more thing, about these clock jitters. This clock jitter is really, can be causing from the noise from the clock generator, right? The clock generators typically is done by some kind of phase lock loop. So that's the most typical case when how people generate the clock, right? And unfortunately, this jitter is not just coming from the source, right? It's also coming from, when you do the clock buffering, right? So when you have the source, you generate the clock, and afterwards you do the buffer. All those circuit blocks, they unfortunately will introduce additional noise, just like what we analyzed in 536A. So you're always adding on top. And then to make it even worse, if there's any noise coupling, right? So let's say you're routing the clock and then there's some other noise source, you couple to the line, it will also cause the jitter, right? So it's basically coming from everywhere. So that's why it's so difficult, right, to ignore this clock jitter, right? So that's why, you know, when we design the track and hold circuits, you know, we have to really take a deeper look on this clock jitter. Okay. So as I mentioned before, you know, one way to sort of find out the specification on the clock jitter is to say that, okay, we look at the worst case, you know, input slope case, right? And then you make sure that, you know, the induced error will be less than 1 LSB, right? So in the case in the previous slide like this, where is the worst case jitter can induce the voltage error? So if you look at this, where do you think that will give you the worst case?
Near the middle point, like near the zero crossing?
Yeah, so you look at this, you know, you basically just look at the slope. So it could be, for example, can be here, you know, the slope looks very sharp, or maybe just right around the point that I was showing you earlier, right? And certainly it won't be here, because here you see the slope here is very flat, right? If I'm pointing to the very bottom, right? Okay, so it really depends on the signal, right? So your signal property can be different. However, you know, if I consider the input as a sine wave, right? The sine wave like that. So where is my worst case?
Near the zero crossing of the
So they will be near the zero crossing, right? Because, you know, at the zero crossing point, that's where the sine wave has the sharpest slope, right? So that one's absolutely correct. You know, if your input signal is a sine, cosine, you know, basically sinusoidal, the zero crossing point always give you the sharpest point, right? So you basically just find a derivative at this point, and you find the dv dt, you multiply by delta t, and that's the delta v, right? And then you use that, you say that, hey, you know, in the very worst case, that jitter-induced error is still less than 1 LSB. Then you know what? Most likely your ADC, your sampling will be fine. Your sampling circuit of the ADC will be fine, right? Because you really constrain that to be less, you know, even in the worst case. In the best case, of course, there won't be anything induced, right? Like here, like what I said, right? So if you sample here, even if there's a little bit jitter here, you know, you see that it doesn't change that much. So that error is very, very small, right? So it really depends, right? It really depends. Okay, so that seems fine, right? So we can, so actually that's what people do, right? So if you want to have a quick estimation on what's the jitter tolerance, so just find what's the worst case and say, hey, you know what? Just make sure that will be less than 1 LSB. However, you know what? It is way too conservative, and you probably can guess this, right? Because like I said, you know, if you look at the, you know, slow varying region, you know, the jitter doesn't really affect anyways, right? And we understand that the signal to noise ratio is sort of the average sense, right, across different sample, right? So sometimes it's really bad, you know, I understand that, but sometimes it's also pretty good, you know, because the slope is actually not as sharp. So we just need to consider, you know, all that, you know, and the bottom line is that, you know, how do we analyze sort of this average sense of the signal to noise ratio, right? So that's kind of the purpose, you know, right now, you know, we want to find out, is it possible to derive the equation for the signal to noise ratio? All right, so to do that, you know, if I assume this delta t, right, which is the clock jitter, right, as I mentioned here, delta t is a random variable, and then this induced error delta v, that should also be a random variable. Okay, so in order to find the power of the random variable, you know, as you probably remember from your random process class, right? This will be basically calculating the variance of the random variable, right? So you calculate the second order statistics, right? The delta V square, and you find the mean value of that, right? The mean value of the delta V square. So that could basically give you the variance, right? The variance of the random variable. Okay, so that basically would tell you what's the power, right? That's the power of that random variable. All right, so now, from the previous slides, we know what is delta V, right? So remember, we do this linear approximation, right? Delta V is basically dv in dt, right? You take derivative times delta t square, right? Times delta t square. Okay, so what is this, right? So I have a basically derivative of the input times the clock jitter, right? So here's the question, right? Is the derivative of the input dependent on the clock jitter, or you think that they are independent? The derivative of the input signals, is there any correlation to the clock jitter? Any guess?
They shouldn't be correlated.
They shouldn't be, right? Because remember before I mentioned that the clock jitter is coming from your clock generator source, maybe coming from the noise coupling, from clock buffer. So they are independent. They are not really related, right? So because they are independent, so we can separate them, right? So we can say that dv dt square times expectation of the delta t square, right? So we basically just separate the two terms. dv dt is 1, and delta t, which is basically the clock jitter, this will be the second one. Okay. All right. So right now I'm just going to, in terms of this analysis, I'm gonna assume that my input is sine wave, right? So we have done this before. Remember when we calculate the SQ and R, right? We also assume the input is a sine wave, right? So the same thing, we're gonna assume the input is a sine wave. So if that's sine wave, so it actually, let me write down. So V in here is A times cosine omega t, okay? So that's kind of my assumption. Then dv dt, so cosine derivative is what? Cosine omega t, if I take derivative, that equals to omega times sine omega t, right? So this is a omega sine omega t squared, right? Times expectation of the delta t squared. Okay, so what is delta t, right? So delta t is actually the clock jitters, right? And typically, the way that we model the clock jitters, typically we model that as a zero mean Gaussian variable. Okay, so mathematically, we can write that this is a Gaussian distribution, and with zero mean and with standard deviation of sigma. Okay, so let me call it sigma t. Okay. All right. So that's a Gaussian variable, and so that's why if you look at the variance of the Gaussian random variable, basically that will give you sigma delta t squared, right? So you just basically square your standard deviation. Okay, so we are almost there. So now we can start to expand this equation. We can take out the constant term, so a squared, which is the amplitude of the input, and also the frequency of the input, right? Omega squared times expectation of sine square omega t times sigma delta t squared. Okay, and so what's the average of sine square omega t, right? So we know that sine square omega t is 1 minus cosine 2 omega t over 2. Right? So if we look at the average of this, cosine, if we take average, it's gonna be 0. So basically that expectation of sine square omega t, basically that's just 1/2, right? So we get a square omega square over 2 times sigma delta t square. Okay, so that's the variance, right? So we know omega is a signal frequency, so I'm just gonna write down as a 2 pi f signal square. Okay, that's a signal frequency over 2 times sigma delta t square. Okay, so that's the noise power. Basically, that's the we just calculate the power of the jitter-induced noise. Okay, jitter-induced. Here, I'm not calculating any quantitative noise. I'm not calculating any thermal noise or anything like that. This is strictly just from the clock jitter, right? And of course, we make a very important assumption. We say that it's a Gaussian distribution, right? Gaussian distribution with zero mean, with standard deviation of sigma t, right? Sigma delta t, sorry, so I should say sigma delta t. Okay, so now we are ready to calculate the SNR. So SNR, as we know, is the signal to noise power ratio. So 10 log. Okay, so what's the signal power, right? If my input is A times cosine omega t, so what is the power of that?
Half a squared.
So this is A squared over 2, right? So that's the signal power divided by the noise power. Okay, so noise power, there's no problem. We just calculate. So this is half A squared 2 pi f signal square times sigma delta t square. Okay, so what is this? So you get 10 log. Here you can see that a squared, they cancel out, right? So a squared, so basically the input amplitude, that term cancel out. So what you will end up with is just 1 over 2 pi f signal square times sigma delta t square. Okay, so this is a very interesting result because what this is telling you is that, hey, if you consider the clock jitter for your sampling circuit, sure, you can calculate the corresponding signal to noise ratio. And what this is telling you is that it's just a function of the signal frequencies. And of course, it's a function of how large your clock jitter is, right? The standard deviation of your clock jitters. But it has nothing to do with your input amplitude, right? So why is that, has nothing to do with amplitude? Right, because you would think that, hey, the input signal amplitude, is larger, feel like, your noise should also be larger, right? So what this is telling you is that, hey, even though the noise amplitude can be larger, but you know what, your signal amplitude is also larger, right? So they kind of cancel out, right? So that's why you see it has nothing to do with your amplitude, right? So amplitude term is crossed out. So and then it just come down to input signal frequency and the clock jitter, right? So this is a very important result because this tells me that if your ADC, right, or your sampling circuits are dealing with a very high frequency input, you got to be careful, right? Because this is what this equation was suggesting, right? So the higher the frequency, the lower your SNR will be, given the same jitter standard deviation, right? On the other hand, if your input frequency is fixed, and then you want to improve your SNR, then basically you just need to reduce your clock jitter, right? So you can do this kind of calculation, and then you can go back to the whoever designed that clocking circuits, right? He told them that, hey, you know what? I think you should reduce this jitter, right? You reduce that jitter. Okay. So that's the signal to noise ratio, and then and here I basically just plot that equation that we just derived in MATLAB, and nothing else, right? So in these slides, I'm just showing you this is the SNR equation that we just derived versus this is the signal frequency. Okay, so I sweep the signal frequency, and then I calculate what's the SNR, and then this is the standard deviation of the clock jitter. Okay, so sigma delta t. All right. So as you can see, what are we learning from this curve, right? So as I sweep the sigma delta t from 10 pico to 1 pico to 0.1 pico, you see this SNR line become higher and higher. You see that? Become higher and higher. Does that make sense? So when I reduce the standard deviation, that means that your jitter is reduced, right? And if your jitter is reduced, yes, your SNR should increase, right? Should increase. All right, so that's one thing that we learn, right? That we learn, and then every time, if I fix the same signal frequency, and then if I improve the clock jitter by 10 times, how much improvement in the SNR I should expect for the same
20 dB?
20 dB, right? So do you see the gap here? The gap here, the gap there, right, is 20 dB, right? Right, basically from that equation, right? So every time you improve by 10 times, that gives you a 20 dB more signal to noise ratio. All right, so that's that's on the vertical, right? So now, if let's say, the clock jitter, unfortunately, you cannot improve. So it's fixed, right? So it's fixed. Then when you increase the signal frequency, you see this SNR trend line will just keep going down, right? So what is the slope here?
It's also 20 dB per decade, right?
20 dB per decade. Okay, let's check is that correct. So from this point to this point, right? So it's about 10 times frequency drop increase, right? And I think this is about 20 dB down, right? So that's right. So it's 20 dB per decade trend line, right? So those are two important things to observe, right? So basically, whenever you increase the input frequency, your signal to noise ratio will go down, right? And this is why whenever you design for high-speed ADC, you really try to sample very fast, which suggests that your input frequency can be also very high, right? Because if you consider a Nyquist sampling, right? So what's the maximum signal frequency that you want to sample, right? Given fs, right? So that's your Nyquist frequency, which is fs divided by 2, right? So if you sample faster, that suggests that your input maximum frequency would also increase, right? So that's that's why for the high speed ADC, we people actually care about this, right? The clock jitter, right? So that would actually affect your performance. Okay. So by looking at this, if let's say I want to design for 10-bit ADC, right? And then if I want to simple, let's say 1 gigahertz input, right? So what is the clock jitter that we should design for? By looking at this chart, roughly, right? So 1 gigahertz, 10 bit. So 10 bit ADC, what's the SQNR, right? It's about 60.
Yeah.
62, yeah. Right? So around 60. So you look at the 60 line here, and then you find that 1 gigahertz, which is here, right? So you see, close to that point, your clock jitter should be around 0.1 picosecond standard deviation, right? So just right there, you get a feeling of how difficult it is, how challenging it is, to design for high-speed ADC, right? And then this further confirmed that, I mentioned that before, the higher the speed you're trying to design, the resolution usually will drop, for that reason, because you can see it's very difficult to maintain a 10-bit resolution at 1 gigahertz, right? So now, of course, if you are waiting to drop your resolution requirement, right, instead of 10 bit, let's say you drop to 7 bit, right? So 7 bit ADC is about what? About 40 dB, right? So if you look at this, about 1 gig, yeah. So I think you can relax your clock jitter to be around 1 picosecond, right? So that's how important it is, to look at this chart and to realize, okay, roughly what was your clocking requirement, right? Typically, by the way, for the low frequency ADCs, usually this is not even a concern, right? Because you can see if you go from the left side, even for 10 picosecond, clock jitters, you can still get a very decent, signal to noise ratio, right? 70, 80, that kind of range, right? So if you're designing for ADC for low speed application, for IoT, for biomedical, usually you are sort of designing for the left side regime, and then you worry a lot less about this, jitter, right? So, okay. All right, so here's a question for you guys. So if I design this ADC, right, and remember that we collect the ADC output, and then you do the proper, windowing, and you select the proper, frequencies, and you plot the ADC output SNR versus F-in, right, or F-sig, right? So basically what I'm doing here is that, I keep sweeping the input sine wave frequency, right? From very low frequency to very high frequency. What do you think that I should see, for the ADC performance?
Well, the SNR should deteriorate with the frequency, like it should be a slope of should be line going down, basically.
Right. So when the F-sig, when the signal is low, right? So certainly, you understand that there's gonna be a trend line here, because of the jitter, right? So whatever jitter, that will be bounded. And then you also have this, let's say, SQNR, because your SQNR, does it matter that, what is my input frequency is? The SQNR. Remember, we derived SQNR is
it's always square. Like delta square over 12, so it doesn't depend on the frequency.
It's independent, right? So
yeah.
So the green line here, let's say this is SQNR, right? So it's independent of the signal frequency, but then the red line, that's is dependent on the frequency because of the clock jitter. Okay, so what is the final SNR of the ADC? Right, so you have two lines. One is the red, induced by the jitter. The other one is just the Guangdong noise. So what do we expect? The final ADC output SNR, right? So in this case, of course, we cannot just expect that the SNR can be higher than that, right? Because the when you calculate SNR, you should compute all the noise floor, right? So in the end, you're gonna see the composite of this, right? So this will become like this. So the purple line is more like what you're going to see for the final ADC output. Signal to noise ratio over F signal. So this is very interesting because if you look at the very high frequency, right? When the signal frequency is very high, what is the slope here?
20 dB per decade too.
20 dB per decade, right? So as it turns out, in the ADC design, only clock jitter will contribute to this 20 dB per decade drop. So very surprisingly, because there are like tons of error mechanism, but it turns out there's only one mechanism that would dominate this 20 dB per decade drop in the signal to noise ratio. And because of that, that's exactly how people back calculate what is the clock jitter of your ADC, right? Because you can look at this trend line and you can fit back, to the curve that I'm showing you here on the right hand side, and you can back calculate what's your sigma delta t. Does that make sense? Right. So that's exactly how people are basically calculating what's the clock jitters, because it's not always possible for you to directly measure the jitter of the clock, right? And there are of course some circuits that would allow you to measure those clock jitters, but not always, right? So but don't worry, once you understand at this level, you can actually use this trend line, over the signal frequency to sort of back calculate, what is your clock jitter, right? And that's also how the industry product, how they, back calculate to say, hey, you know what, this ADC that we have in our product, the jitter is less than, let's say, 1 picosecond. So that this is how they calculate the clock jitters. All right. Any question? So this is very important. And I think I mentioned that in the first class. These days, there are a lot of applications, really pushing for high speed link, either wireless link like 5G link or wireline, right? The optical transceivers. So people are actually pushing to this region right now. So this is no longer something that we just for the sake of teaching the class. This is real right now. This is where the region that one day you graduate, you go to industry, you start design your design job. This is the region that you are dealing with right now. So this is again, this is just not for the sake of deriving those beautiful equations. This is actually the region that you will be working, right? I mean, if you work on those high performance circuits in the future, right? So okay, the last topic I like to talk about regarding the track and hold is on the noise. Okay, and as it turns out that because we talk about this noise in 536A, so this is going to be very trivial for you right now. Okay, so if you consider this track and hold circuits, right? This is the simplest one, right? So we say that there's a sampling switch here, and then we also have the sampling capacitor, right? C. And in the tracking mode, right? In the tracking mode, we now know that this sampling switch is in trial mode, right? In trial mode, so the trial mode resistance is R on, right? And then I think you guys point out that in the tracking mode, this is basically a low pass filter, right? You have R and C. So in this kind of systems, you know, you have 1R, 1C. So where is my noise source? Basically, these are 536A questions, right? So where is the noise source?
R.
So the R, right? So you have R, and then you know this R has this what 4 kTR, right? Noise, the density, right, per hertz. So 4 kTR, you know, is the noise density, right? And then you basically just find the transfer function. Remember in 536A, right? So you have the noise source, you find the transfer function, right? And then what do you do? The noise source multiply by your transfer function, right? Your transfer function is this, right? Because this is basically like a voltage divider, right? Divide between R on and 1 over J omega C, right? Does that make sense? So you use that, you find the transfer function, and just don't forget, you know, you have to look at the magnitude of that transfer function square, right? Square, right? So this one is 1 over J omega C over R on plus 1 over J omega C, right? So that's a transfer function. And just don't forget that, you know, you should look at the magnitude of this transfer function and take a square, right? So that, you know, will basically come to this equation, right? So you have this integral of 4 kTR times the transfer function square. And then what you do is that you integrate from DC to infinity, right? From DC to infinity. So that's pretty much what you need to do, right? Okay, and then just come down to R and C, and then we don't need to derive this. I think we kind of went over that, you know, in 526A. So it turns out that the R cancel out, so it's independent of the resistance, and then it just come down to KT divided by C, right? So this C, I should call that CH here. CH is the capacitor, the sampling capacitor here. So it'd be KT over CH, right? So that's the sampling circuits, you know, in terms of the noise, right? The thermal noise that will get sampled onto the capacitor. Okay. So here's a question for you, right? So what's the tolerance on this KT over C noise? Right, because this is equivalent to you have a signal and I take the sample, right, at this point. But on top of that, I'm adding a little bit noise, and then this noise I'm adding here is actually KT over C, right? The power, right? The power of it is KT over C, right? So let's say, okay, so let's say if I make this KT over C noise roughly equal to delta square over 12, let's say, right? So this KT over C, I just say, hey, you know what? Let me just make it roughly the same as delta square. By the way, delta is the LSB, right? LSB square over 12. If that's the case, then what is my SNR or SNDR compared to SQ and R? So what is my
they are uncorrelated, so it's gonna like be
by
doubled.
3
The noise will be doubled. So
right? So the noise will be double, right? The noise power is double,
Yeah.
right? Because this is power, right? So the power is 2x. So that means that the SNR should goes down by how many?
3 dB.
Half.
3 dB, right? So this is go down by 3 dB. That's exactly right. Right? So just keep that in mind, right? So if you design this KT over C, and then you say, hey, you know, that's the capacitance that I need to design, and then just make sure you understand that, you know, if you make this KT over C equals to delta square over 12, right away you degrade SNDR by 3 dB. Okay. If my SNDR degrade by 3 dB, that means that my ENOP degrade by how much? Enup means the effective number of bits, right?
0.5 bits.
So 0.5 bits, right? So this goes down by half a bit, right? So for that reason, you remember I mentioned in real life, it's impossible for you to get the SNR to be equal to SQNR, right? SQNR is the highest upper bound. And as you can see, if you design KT over C is just roughly equal to delta square over 12, you degrade by half a bit already, right? So that's impossible that you get SQNR value, right, in the final ADC. All right. Okay. So so let's do a quick examples, like for calculations. So let's say if I'm designing for 18-bit ADC, and if I want to sample at 100 megahertz, so 100 mega sample per second. Okay, and then if I just do this calculation, I do KT over C roughly equal to delta square over 12. You will end up that sampling capacitor size will be roughly 3.4 nanofarad. Okay, that's how much how large you need to design for that sampling capacitor. Okay. All right. So then you say, hey, yeah, from this noise perspective, now I can determine the size of the sampling capacitors. But what about R on? So how do I know what's R on I need to design for? Right, because we now know that this noise is just a function of C. It's independent of R, which is kind of nice. So I don't need to worry about the turn-on resistance. But of course, when we design the real sampling circuits, we have to determine what's R on, right? So in this case, how do I determine R on? So what would limit the R on? So if you remember, we talked about earlier, right? On the remember this? The tracking time, the settling, right? The number of the time constant R times C, right? So it depends on how many bits you are designing, right? And then how many time constant you need, right? And how much time you can have for the tracking time, right? So you can use this to back calculate, right? So let's say I need to do 7 tau, right? 7 times the RC, and now you know the C, right? Because from KT over C, you find out what's the C. So you can back calculate what's your R. Does that make sense? So you can calculate what's R on. So in this case, if I assume that I use half clock period, so my clock period is 100 megahertz, right? And if I just use half of them for the tracking time, right? And I calculate 18-bit, so you can calculate how many tau you need. That's a lot of a number of tau that you need, right, for the tracking. So if you back calculate, you know what, your turn-on resistance has to be as small as 0.1 ohm. So that's very small value, right? So so I hope that you can appreciate how difficult it is to design a sampling circuit just like this, right? So still come back to the same conclusion, right? So whenever you design the ADC, you're pushing for the more bits, more resolution. You have to respect that person. You seriously have to respect that person. 1 more bit, you bow to him or bow to her by another 10 degree, right? So, and if that person designed the ADC or double the speed, you also need to bow to that person, by another 10 degree, right? So that just just come down to the very fundamental trade-off. How difficult it is to design the circuit in that region, right? Versus if you do in the very low power regime, then you don't have this constraint. Basically, what you do, you just minimize the power consumption, right? So just a different trade-off. All right. Here's a number that is good to have. So your guideline, right? So if if your capacity is 1 puff, right? So KT over C at the room temperature, this will give you about 64 microvolt. These are RMS, right? So standard deviation, right? So square root of KT over C, that's about 64 microvolt, right? So sometimes people feel this is convenient to remember, right? Because, for example, if your sampling cap's 4 puff, right? So 4 times, that means that your noise power will go down by 4 times, right? That means the standard deviation will go down by 2 times, right? So if you say that, okay, 4 puff, then there will be 32 microvolt, roughly, right? The standard deviation. Yeah. So sometimes people use this to remember. Just like when we talk about 536A, right? We say that 50 ohm, right? What's the 4 kTr for 50 ohm, right? So same thing there. Okay, so that just gives you a rough sense of what's the noise magnitude related to the sampling capacitors. And by the way, it's not always that when you design the ADC, you always need to worry about this. As you can probably imagine, if your delta is very large, right? So what does that mean by delta is large? Your delta is your LSB, right? So if you are designing for the modest ADC resolution, you pretty much don't care about KT over C, because no matter what the sampling capacitor that you are using, it ends up will be much less than delta squared over 12 anyways, right? So in those kind of regime, so that's what I'm saying, right? So if you are not pushing for high resolution ADC, you're not pushing for the high speed, a lot of things are become easy, right? You don't need to really worry about those, right? So in those regime, you don't even really care about this noise. I mean, it will be there. I shouldn't give you, a fake impression that it's not there. It is there. It's just that it's negligible, right? Does that make sense? So it's just negligible. So to that extent, you basically don't care. But it will be there. It's just that it's negligible, right? So it is always the high resolution. When you design ADC for higher resolution, that's where you normally would care more about this KT over C noise. Okay, for the KT over C. All right. Any question? Okay, so if not, yeah, so that concludes the first part of the sampling circuits. And now we can move to the second part, where I'm going to discuss a little bit more techniques, to improve the non-ideality, right? Because in the part 1, we really examine a lot of different non-ideality, related to the track and hold or sample and hold circuits. Of course, we discussed several techniques to, in terms of how to do the proper sizing, right? Just so that we can meet the spec. But that those are not the only way, right? So it's more like brute and force to do the proper sizing. But of course, there are gonna be a lot of different approach that we can mitigate those effects, without necessarily, making the devices too large, and things like that, right? Okay, so that's the point of the part 2 of this lectures. Basically we want to see what are the different useful techniques to improve or to mitigate those non-idealities. Okay. So the first one is the CMOS switch, and I believe some of you actually kind of hinted this, when I was talking about this single switch sampling circuits, right? So some of you already say, hey, you know what? Why don't you use CMOS, right? So, and in a digital circuit, we call that a transmission gate, right? Transmission gate. So yeah, so that you can do that, right? So instead of using a single MOS switch for the sampling circuits, you can use a pair, right? You can use MOS and PMOS, and you do in parallel, right? So in this case, this R is going to be the on resistance for the MOS in parallel with the on resistance of the PMOS. Okay. And again, if we assume this is a square law device, which we know is not, but if we assume that's close enough, right? And then we just want to get some insight. So you can see this will be the on resistance from the MOS, which is mu n Cox W over L MOS times VGS n minus VTHN, right? In parallel with the PMOS version, right? The PMOS version, the on resistance of the PMOS is mu P Cox W over L PMOS times VGSP, and let me take the magnitude, minus VTHP magnitude. Okay. All right. So these two on resistances are in parallel. And so you have to inverse, right? So 1 over inverse of the RRN and 1 over RP. So if you sum that up, what you're going to get is mu n Cox W over L VGSN minus VTHN plus mu P times Cox W over LP, sorry, and previously it was W over LN times VGSP minus VTHP. Okay, so that's the combined turn on resistance, right? Of this transmission gate, basically, right? MOS and PMOS. All right, so this is my V in, right? So for the MOS, what is my VGSN? My VGSN here, input is V in, right? And the gate voltage of the MOS is what in the sampling mode, right? In the tracking mode. This is VDD, right? So this will be VDD minus V. Okay, so that's a gate source voltage, of the MOS. What about the gate source voltage of the PMOS, right? In the tracking mode. So in the tracking mode, the gate of the PMOS, usually we tie that to ground, right? Tie that to ground. So the VGSP here is basically just V. Okay, so it ends up that you're gonna get something which I'm not gonna rewrite, but I would like to focus on the term that related to V in, right? Because I have a V in VGSN, I have a V in VGSP. Okay, so if I just factor out the V in term, so I'm going to get mu P Cox W over LP minus mu n times Cox times W over L n. Okay, and like I said, you should just write the other terms on the left side, which is independent of V in. Right now, of course, I'm more focusing on V in because for the reason that we mentioned before, right? Because we don't want this on resistance to be dependent on V in too much, right? We want this to be relatively independent, right? So I do not want this V-in dependency, into this resistance. Okay. So by looking at this, how do I minimize? How do I minimize the impact of V-in onto this resistance?
If you choose the sizes of the P to compensate for the difference between them, like if you choose mu multiplied by W over L is equal in both sides, we can minimize that effect.
That's right, right? So if you choose the mu W over L P and W over L N, basically inverse to the mobility ratio, mu P and mu N, right? Then they cancel to each other. You see that, right? So if the mobility of the PMOS, usually mobility of PMOS is larger or smaller than the mobility of the MOS.
The MOS is larger.
MOS is larger, right? So which means that we should size the MOS W over L to be
Smaller, yeah.
smaller, right? Smaller, right? So does that remind you of the inverter sizing?
Yes, exactly.
Right? So the inverter sizing was exactly doing the same thing, right? So we size that inverse to this mobility ratio. So that's the bottom line here, right? So not only we just do a transmission gate, right? As we mentioned before, that you can flatten out. You could actually do a proper sizing, right? So size this between MOS and PMOS, right? Such that this term disappear, right? That would be the best. If you make this disappear, which means that they cancel out, then you basically just minimize the dependency, right? So then this R will be flat, right? Which is perfect, right? Because you don't have any dependency. Okay, so that sounds pretty good, so you basically just size that, pretty much just like inverter sizing. Of course, as you probably can guess, in real life, this is impossible to have a perfect cancellation, right? I think that probably makes sense. You can probably, everybody can guess that, it's very hard to perfectly cancel. And why is that? So in real life, of course, things won't go as exactly as perfectly as what we just derived, right? So several things, right? So here, obvious reason is that we assume it's a square law device, right? So in real life, it's not square law, right? There's a lot of short channel effect, right? So the equation won't be exactly like this. So that's why it cannot be perfectly canceled out. Another reason is that even if I design this MOS and PMOS sizing, right? So let's say inverse proportional to this mobility ratio. The problem is that there's gonna be a mismatch, right? Between the MOS and PMOS. So even though you say, hey, W over L is 5 for MOS, and W over L for the PMOS should be 10, but when you send this to TSMC, the chip come back from TSMC, it won't be exactly like that, right? So any mismatch between this MOS and PMOS is going to cause this imperfect cancellation, right? Imperfect cancellation. Another thing that we kind of ignore here is the threshold voltage. You see VTHN and VTHP, I kind of move that to the left-hand side, right? Because it's a VTH is independent of the being, right? So in reality, is the threshold voltage of the MOS and PMOS dependent on Vin? What do you guys think? Would the threshold voltage of the MOS and PMOS here is a function of Vin?
No.
Right, so ideally it should be no, right? But then if you consider the body effect, right? So I think that's basically come down to when I connect the MOS, where's the body of the MOS usually I connect to? Usually connect to ground, right? And then the body of the PMOS usually connect to VDD, right? So if that's the case, please don't forget about the body effect, right? The body effect. Right. So the body effect, unfortunately, it will affect your threshold voltage. So just keep that in mind, right? So it's a weak function, right? So this VTHN is a kind of a weak function of the Vin, and likewise, this is also a weak function of Vin. So kind of like a second order effect, right? So if you have this second order effect, and you factor that in to that threshold voltage, then unfortunately, even if you do the sizing according to the mobility ratio, you are going to see some dependency on being, right? So the bottom line is that, that turn on resistance of that switch, it still cannot be a flat line, right? So that's the bottom line. And then because that's not a flat line, and as we discussed in the part 1 of the lectures, you are going to see some distortion, right? Harmonic distortion. Okay, any question? If not, I think this is a good point to have a short break. Yeah, so let's take a short break, and when we come back, we'll continue to discuss the other techniques to improve the sampling circuits. Okay. Okay. So let's continue. All right, so so that's how the transmission gate, right, or CMOS switch can help to improve or mitigate the signal dependency, right? So basically, don't want those V-in term, to show up in the on resistance. Another benefit of doing the CMOS switch, right, the sampling switch, is that we can also mitigate the pedestal errors, right? The pedestal error. Remember, we talked about pedestal error. It's coming from the charge injection, coming from the clock feed-through, right? And I think one of you in the class already pointed out, by having this MOS and PMOS together can improve the charge injection, right? So let's take a look, right? So for the charge injection, for the MOS, we know it will be like this, right? So it will be high to low, and for PMOS, it will be low to high. So if you consider the clock feed-through, right? Remember that's mainly going through the overlap capacitance. So you can see, when they come here, one will go down, the one will go up, and they kind of cancel out with each other, right? So the clock feed-through, we roughly cancel out, for having this MOS and PMOS. And for the charge injection, it can also improve, right? Why? Because if you look at the channel charge for MOS, the carrier is the electron, right? So electron means that's negative charge, right? And for PMOS, it's the opposite, right? For PMOS, this is the host, right? So host is a positive charge, right? So when you have this channel charge, and then in the case, obviously, in the fast gating, right? So the channel charge has nowhere to go. We can assume that it will split into half and half. Remember, right? Half go to the source, half go to the drain. So half. So you have this negative charge, you have the positive charge. So when you sum them together, right? So as you can see, the MOS has a negative charge, PMOS has a positive charge. When you sum them together, they could roughly mitigate with each other. Of course, that depends on the W times L product, right? So W times L, so WNLN, WPLP, right? And also this VGS, right? So VGS minus VTH, right? So on this. So you can take a look, right? So it will help, to reduce it, just because it's a opposite polarity. If you want to further to actually say that, okay, you want to cancel them out, so you can do a similar thing as well. We checked in the previous slide. Instead of look at the W over L ratio, you actually look at the W times L product, right? Product. And then also the relative relationship between the VGS minus VTH. Right? So that's how you can, take a look, to see whether you can reduce this pedestal error, right? So just a lot of benefits, by having this sort of a MOS and PMOS pair, as a sampling switch. Okay, any question? All right, so next useful technique in terms of the sampling circuit is something called clock boosting. Okay, so basically the idea is that, so let's go back to the single transistor, right? So just a single MOS transistors as a sampling switch, and you go into the capacitor. Okay, so here, before we say that, the gate voltage to the switch usually is between 0 to VDD, right? To VDD. right? Because that's usually the power supply that we have. Okay, VDD, if that's 5 volt, okay, that's 0 to 5 volt, right? So that's what we have. Okay. And what if we increase the clock swing, right? So instead of to VDD, we increase that to m times VDD. Okay, so we actually multiply up. Okay, so we make a higher VDD. If I make the clock swing higher, right? So in the case of a MOS sampling switch, so the gate voltage in the tracking mode will be higher. What is the impact to the on resistance? Right, so here, again, I assume that's a square law device, right? So the turn on resistance in the trial mode will be 1 over mu Cox W over L times this M times VDD minus V in minus VTH, right? So minus V in minus VTH, that's exactly the same as before. The only thing that changed right now is just this M times VDD factor. Of course, in this case, M is larger than 1. Right? So because I want to increase the clock swing. Okay, if I increase the clock swing, so this M times VDD is larger than VDD, what is the impact of in relative to that V in, to the R on, right? So assuming that my input swing is still the same, right? So let's say V in is changing from 0 to 100 millivolt, right? So that remains the same. The fact that I increase this M times VDD, and then even though this V in is still changed, let's say, 100 millivolts, my impact to the variation of the R-on will be smaller or will be larger. If I increase this, it will be smaller, right? Because you see, because the M times VDD is larger, so this 100 millivolt relative to the entire M times VDD will be smaller, right? So that, to that extent, this clock boosting can actually, we call it clock boosting because we are really trying to increase the clock swing. It will decrease the dependency on V in, right? That makes sense. So that's one benefit. Another benefit is that, would this improve or reduce the resistance value?
Reduce.
It will reduce, right? So even forget about the dependency on the V in. The fact that, you increase the swing, right? The gate voltage, the on resistance also reduce, right? So on resistance reduce is a good thing or not a good thing?
It limit the bandwidth, so like the less the better.
Less the better, right? So remember the RC time constant, right? R times C, right? So if you are able to reduce the resistance, you can settle faster, right? So the number of tau, that tau value now is reduced, right? So there are also, that advantage, right? So that's why, clock boosting is useful, to reduce the distortion and also can reduce the absolute value. So let me write down absolute value of R-on. So essentially you can enhance your tracking bandwidth. Right, so that can be very helpful, right? Very helpful. In reality, even though we say that, hey, we should, increase the clock swing, but the question is that, can we increase too large? Right? Can we increase this to 100 volt, for example? Right? So probably not, right? So even though we know this is the higher the better, but if you make it too high, you may actually break the device, right? So typically we limit that to 2. Typically, so the outer bound usually we limit to twice VDD, just because we do not want to break down the device. You want to avoid break down the device. Okay. So that's also important, right? So on one hand, we want to reduce the arm resistance, we want to reduce the distortion, all that is fine, no problem with that. But let's don't forget, we also need to keep our circuit alive, right? So sometimes, as we are trying to improve that, this can be, overlooked, and then the circuit can be broken. Okay. Okay, so that's the clock boosting concept. So the question now is that how do we do it, right? So how do we actually do it? So here's one example. There are, of course, different way of doing this. This is a very typical way of implementing this called clock boosting, right? Clock boosting. Okay, so the circuit is as follows, right? The incoming clock is here on your bottom left. So the clock here is 0 to VDD. Same as before, okay? So the clock here is 0 to VDD. On the right-hand side, this is your sampling switch, right? This is sampling switch. And the gate voltage of the sampling switch, VG here, that's the one that we want to increase. We want to increase, okay? And therefore, we have this network. Basically, as you can see, you have two capacitors here, right? And then the clock coming to inverters, right? So you first invert the clock. So this is, you can think that of as a clock bar, right? Clock bar. And the other side of the C1 and C2, you connect to the cross-coupled NMOS, right? M1 and M2. And these two NMOS is connected to VDD, okay, to VDD. And on the right-hand side, you see this M3 and M4, one's PMOS, the other one's NMOS. It's driven by the 0 to VDD clock, right? And then it's sitting between this the sampling switch and this capacitor node. Okay, so now we're gonna study this. Okay, so let's do slowly. Okay, so first there's a clock, and the clock is basically 0 to VDD. Okay. And then there's a V1. V1 node is the other side of the C1. And then there's a V2, which is on the other side of the C2. And then there's a VG. VG is right here, right here. Okay, so how does this work, right? So in the beginning, when clock is low, right here, and then this clock bar will be high, right? In the beginning, if this is 0, and then this is high, right? This VDD. And for now, I'm going to assume there's no initial charge on C1 and C2, right? So there's no voltage drop there. So this C2 initially was reset, so there's no charge across that. So V2 to begin with will stop on VDD, right? In the beginning is VDD and this is VDD, right? So V2 is VDD. So when V2 is VDD, what is V1 in that case? So V2 is VDD. That means that V2 go to the gate of the M1. M1 transistor is the MOS, right? So if the gate of the M1 transistor is VDD, what happened to V1 node?
It will start to increase because the device will be on.
The device will be turned on, right? So M1, yeah, because the gate is tied to VDD, right? So that means that V1 will try to get connected to VDD, but can that go all the way to VDD? That was the question.
Assuming no, it will go all the way up to VDD minus V threshold. That's when the device will turn off.
That's right. That's right, right? So again, here we just assume there's a square law device, right? So VDD minus threshold voltage. So that's That's how it started. So this would be VDD minus VTH, right? Okay, so in that case, okay, so we figure out the V1, V2, and what about the VG, right? The gate voltage of the switch. Okay, so in that case, okay, let's take a look. So V2 is what? V2 is VDD, right? We said it's VDD. And then the initial voltage in the clock here is ground. So if this is ground, so M3, what happened to M3? M3 is PMOS. The gate
It's
of
on.
M3 is on, right? So it's on. So that means that what? So VG has to be
VDD.
VDD, right? So it's turned on. So VG has to be VDD. Okay, so VG has to be VDD. Okay, very good. And next, of course, you know, the clock will go high. So basically you see this node on the bottom left, the clock, it will transition from low to high, right? So when that's low to high, it will push, and then of course, you know, here will be high to low on the output of a basic clock bar will be high to low, right? High to low. So this V1 here will get pushed up, right? Because, you know, this node right here is going up. So this node V1 will also get pushed up, right? So this will be get pushed up, and then this we don't know yet. So let's leave V2 a little bit later. So just look at V1. So V1, if the other side of the C1 goes up by VDD, that means that V1 would also go up by VDD, right? So if V1 go up by VDD, what is the new value? Before it was VDD minus VTH.
It's 2 VDD minus VTH.
So 2 VDD minus VTH, right? So this get push up. All right, so if V1 get pushed up to 2 VDD minus VTH, what happened to V2? V2 is on the source side of the M2 transistor, right? M2 is the MOS transistor, right?
Yeah,
So
it will be pushed up also by VDD, till like by VDD minus VTH till the M2 closes.
okay, so because here right now is a 2 times, right? 2 times VDD minus VTH.
Oh, so
then-
yeah.
Minus
And
2
then, so
times.
it will be very high, right? Assuming if VDD much higher than threshold voltage. So in this case, the V2 can actually, you know, just connect it to VDD. Does
Yeah.
that make sense, right? So because, you know, I push the gate to be twice VDD minus VTH. So it turns out that this VDD, V2 will be continue to be VDD. No change, because, you know, it will, this is a MOS, right? So this will continue to be VDD. All right. What happened to VG, right? The gate voltage of the switch. Okay, so now let's take a look. So in this case, let's see. So the gate of the M4 right now is high, right? So because the clock goes low to high. And then if V2 node right now is still VDD, and then this is instead of ground, right now go to VDD, right? Go to VDD. Then what do I have? So M3, what happened to M3 right now?
It's off.
M3 is off. What about M4?
It's on.
It's on, right? So M4 is on. So that means that VG will go to
VSS.
VSS. So it will go to ground. VSS, let's go to ground. All right, so far so good. And then afterwards, you know, of course, the clock will go low. Now, when the clock goes low, that means the clock bar will go high, right? Clock bar will go high. And then again, you know, just like what we had, you know, before, you know, instead of V1 get pushed up, right now it's the V2 get pushed up, right? From low to high, right? From 0 to VDD. So that means that V2 before was VDD, and now it will get pushed up to how much?
2 VDD.
2 VDD, right? Because right now it's also get pushed up by 2 VDD. Okay. Now if this, let's take a look. So if V2 right now is 2 VDD, what happened to V1? So right now this V2 is 2 times VDD. That means that M1 transistors, the gate is 2 times VDD. And then what happened to this source side, which is V1?
2 times VDD minus VTH.
Mhm.
You
It
will
will
go
remain
to
the same one basically.
VDD minus VTH, or this will become 2 VDD, right? Because this gate will become 2 VDD.
Mhm.
And assuming the VDD is greater than or much greater than VTH. So now you can actually push V1, actually go to VDD, right? Instead of VDD minus VTH. So this will go to, it'll be lower, but then this will be VDD. Instead of VDD minus VTH, because right now the gate is now twice VDD, right? So this goes to VDD. All right. What about VG? So in this case, we need to see what happened to VG. VG, this node, the gate of M3 right now is ground, right? So this right now is ground. If this is ground, what happened to M3?
It's on.
Is on, right? And then V2 right now is 2 VDD. So that means that VG here is what?
It will go to 2 VDD.
It's 2 VDD. Very good. It's 2 VDD. Okay, so there you go. That's exactly why you get the clock boosting, right? You see, in this case, it doubled, right? It doubled, right? And then afterwards, I don't need to analyze, so you can do that at home. This basically will go down, and this will continue to VDD. So basically, the bottom line is that if you look at VG, which is the gate of the sampling switch, the swing is doubled, right? Instead of 0 to VDD, right? In this, on the top, this is 0 to VDD, label it, right? And now you create a clock that is 0 to twice VDD. Of course, the clock phase inverted, if you notice, right? So when the clock high, now it becomes low, but it's okay. The key point is to maintain that swing that you wanted, right? Even though the phase off by half clock period, that one is fine. Okay, so that is our clock boosting circuit. Very useful, right? So these are very useful tools to improve, as we mentioned before, to improve the resistance, right? To reduce resistance and also reduce the dependency on that input signal, which means that you reduce the distortion. Okay. Next, this is also almost like a cousin of the clock boosting. So we're also trying to play some trick on the clock side, but we are not just boosting up the swing. Okay, we call this as clock bootstrapping. Okay, circuits. So the idea is that before in the clock boosting circuits, when I turn on the switch, I double the swing, right? In that case, right? I basically double the swing. Right now, I don't double the swing. Okay, what I want to do is that I want the gate voltage, so this is a VG node, is exactly V in plus VDD. Okay, so I'm no longer interested in making it twice VDD. I want this gate voltage to be exactly V in plus VDD. So it's essentially that you add a battery between the input to the output, which is a VG, right? So that's why you see this is a battery, right? This is a battery in between. Okay, so what does that do, right? So if in the tracking mode, which means when I turn on that sampling switch, if my gate voltage is precisely V in plus VDD, look at this equation, right? So this is my gate voltage, right? So VGS means that VG minus V in and minus VTH. If I make the gate voltage exactly VDD plus V in, you know what? When I write down this equation, V in cancel out perfectly, right? So that's another approach, right? So instead of just double the swing. By the way, if I double the swing, can I cancel out the V in? So let's go back to this, right? So this is a clock boosting, right? So M times VDD. Do I cancel out V in? I don't, right? I do not cancel out the swing. All I did was just to make sure the V in just relatively small, compared to this M times VDD, right? So that's how the clock boosting scheme works. But now, if I make this clock boosting circuits, which I make the gate voltage equals to V in plus VDD, you know what? If you can design this clock boosting perfectly, which means that your clock is changing from V in plus 0 to V in plus VDD, you can actually cancel out this V in, no problem, right? So that's the beauty of this clock bootstrap circuits. Okay, so that sounds good, and this is one example of how to implement this kind of clock bootstrap circuits. There are, of course, different variations that you can do to do this, but this is one of the most popular one that people use. Okay, so I'm using this as examples. So here you can see, first of all, this is your sampling switch. M1, that's your sampling switch. Okay, and you notice that there are two clock phases, so there's a phi and phi bar. So phi will be like this, and the phi bar is basically the inverted phase, like that. Okay, and one thing I want to draw your attention is this left-hand side. What is this? This circuits M5, M6 is a 2 MOS cross couple, and you have two capacitors, C1, C2, and you have an inverter in between. So what does that remind you of? That reminds you of the one that we just had, right? Remember on the left side, that's how we double the swing, right? So that's exactly what it is, right? So this, at least we can recognize this is basically just a clock boosting. Okay, so we can boost up the node here to be eventually twice VDD, right? 2 VDD swing right there. And then, the rest of the circuit, you do have a capacitor here, C here, that's that is important. So no matter how you vary these clock bootstrap circuits, typically people use a capacitor, basically as a battery, right there. And then of course you have a bunch of switches, and connect to different phases. And the bottom line is that you want to control this gate voltage right there, to be exactly, V in plus VDD, during the tracking mode. Okay, so that's sort of the target. Of course, when we analyze this, there are different steps. So don't worry, we're gonna do step by step. Okay, so first is what we call as a first phase, and the first phase is when phi equal to 0. Okay, so basically what I do is that, here, right, when phi equal to 0, for example, is this switch turn on or turn off? This switch right here?
It's off.
It's off, right? So whenever that's off, then I just don't draw it. So here you can see that I just take out that switch. You understand that? So whatever that is turned off, then I take it out, right? So if this is off, and then this phi bar, for example, is on or off? Phi bar is on, right? So you can see here is on, so I put it there, right? So whatever switch I put here, that means it's on, right? So same thing, this a MOS on the top, that one is on. And then this one, let me see, phi is low. So this is off, right? This is off, but then this PMOS is on, right? Is on, so this is VDD, right? So this node is VDD, so this is off, right? So, oh yeah, so it's already drawn like this. And then there's a phi bar here, you know, this one will be on, right? This will be on. Okay, so this is 1, so this is on. So what is VG? This is VG, right? VG node is, what's the voltage on VG? This is 0,
ground.
right? It's
It's
grounded,
ground,
right? Yeah, because you connect to ground, you know, through this M3 switch. All right, so here at this node, you know, when this is 0, so this go to VDD, right? So VDD here, yeah, so I should have removed this. So this is basically is off, right? Because this tied to gate is VDD is off. And then the phi bar here, you know, is coming from this, which is coming from the clock doubler circuit. So in this case, it's not just VDD, it's twice VDD, right? Twice VDD, because remember we just analyzed that before, you know, the clock here should be double. And the phi bar here on the bottom is not boosted, so it's only VDD, right? So in that case, what is the voltage on the bottom side of this capacitor? So this is turned on, right? So this is ground, right? And on the top side, you know, this MOS gate is 2 VDD. So what is the voltage here? This is MOS, right? So it turn on, so connect to VDD. So this VDD, this node will get pulled to VDD, right? VDD. And then this M2 device is off. So basically, the bottom line is that in the first phase, my VG will get pulled to ground, right? VG will get to ground, and this M2 here in between, they will disconnect between the left and right. And the important thing is, look at what happened to this capacitor during this first phase. The top side connect to VDD, right? And the bottom side connect to ground. So the voltage drop across this capacitor is
VDD.
VDD. Is VDD, right? So that's very important. So basically, you reset or pre-charge this capacitor in the phase 1 to be exactly VDD. Okay. Now, of course, in the next phase, when phi equal to 1, then, you know, again, those devices get cut off, right? This device get cut off, you know, basically whatever that was on before in phase 1, now is off, right? So, but then, you know, you have this transmission gate now is turned on, right? So here, input coming in is V in, going through this gate, come to here. So what is the voltage here on the other side?
VM plus VDD.
V in plus VDD, you see that? So that start to show up, right? And then this M2 right now, the gate, because this is turned on, so this is V in, right? So if the gate of this M2 is V in and the source is V in plus VDD, what happened to this M2 device? This is PMOS.
It's on.
It's on, right? So if that's on, what is the voltage to show up here?
VM plus VDD.
It's still V in plus VDD, right? So there you go, right? So that means that, hey, in the tracking phase, because this is your sampling switch, the gate is exactly V in plus VDD. And that's exactly what we want, right? Because as we mentioned before, you know, the target of this clock bootstrapping, you know, is to make sure in the tracking mode, this clock amplitude will be exactly V in plus VDD. All right, so sorry, I went over a little bit fast, but it's okay. You know, I think at least, you know, I was able to explain, you know, between this phase 1 and phase 2. And when we come back next week, and I think on Monday there's no class, so when we come back next Wednesday, I'll start from here and I'll talk a little bit more to close this topic on the clock bootstrapping. Okay, any question? All right. So if not, I'll see you next Wednesday, and then your homework 2 will come up very soon. Okay.